All right, so here we go. We are going to start chapter 4. Okay, we are going to do some work on a topic called related rates. Not going to lie, it's not everyone's favorite topic in calculus. For whatever reason, I think a lot of people shy away from word problems in general. But it's definitely a big part of the class, and we're going to use some derivatives to find some actual real life stuff that's going on. This is not a lesson where you're going to leave feeling real good about it, probably. Okay, so we're gonna review just like before. You guys will get back into this. There'll be 5 lessons this week, and then next week we'll slow down and we'll do a bunch of reviews. I think it's going to go better because I'm going to be seeing you guys daily, Tuesday through Friday, right? So we'll be Zooming together 4 consecutive days in a row where you'll have time to ask questions and we can do extra problems. Okay, so let's jump in here and talk about it. There's some basic directions here that you can read through. I think they're helpful, but I think that they're a little bit intimidating before you start doing a problem. So I'm going to come back to these maybe while I'm doing some problems. Okay, so before we do this, since it's been quite a while since we've done derivatives, let's do a quick review of implicit differentiation. Okay, so, before we do that, let's just go back even further. We have y equals 4x squared. So then we would say, hey, look, dy dx, this is just normal derivatives. We would do the power rule, right? 2 times 4 is 8. And then we have x raised to the power of 1. And then once we found equations that weren't solved for y, remember, we had this new strategy to take the derivative with respect to x. Okay, and so we're going to take the derivative with respect to x of all of these things individually, term by term. And when we did that, when the variable doesn't match the x variable down here, we had to add in that dy dx. And maybe this will come back slowly. So the derivative of y squared, we would say, well, look, it's 2y. But y doesn't match x, so we have to add in a dy dx. Okay, plus. Now we've got the power rule, right? You've got 2x and you've got y. So to take the derivative of this, it's first 2x times the derivative of the second. Well, the derivative of y is just 1 dy dx. So first derivative of second plus the second times the derivative of the first, which is 2. Okay, plus the derivative of 3y is just 3, but y doesn't match x. And so we have our dy dx equals, and the derivative of 10 would just be 0. Okay, so this is all to remind you guys that you're going to be taking the derivative implicitly, okay? And when the letter doesn't match the denominator of your derivative, you have to add in this dy dx term, okay? This happens in related rates. So looking back at these notes, you are going to take the derivative with respect to time. Okay, so related rates deals with derivatives with respect to time. Okay, that's a really big part. All right, so let's look at this first example. You've got a spherical balloon. It's inflated at a rate of 10 cubic meters per minute. Okay, find the rate at which the surface area of the balloon is increasing when the radius of the sphere is 3. A lot of stuff to unpack there. Don't stress. I didn't put the equations here. The AP exam will always give you equation. So they would tell you here, look, the volume of a sphere is 4/3 pi r cubed. I know you guys probably already knew that. And the area is 4 pi r squared. So the surface area of a sphere is 4 pi r squared. The volume of a sphere is that. Okay. So when we do related rate problems, you're going to keep it really simple. You're going to interpret and write down everything they give you. And then you're going to write down exactly what I'm trying to find. And doing that is going to get you AP points. Okay, so when it tells you a spherical balloon is inflated at a rate, okay, at a rate of 10 cubic meters, that's a volume, right, with respect to time. And so you interpreting this to be dv dt equals 10 would get you 1 AP FRQ point. Okay, so this will get easier the more you do, but they just told us a rate, right? So it's with respect. That's why there's a fraction bar here, right? So that the volume is changing at a rate, dv, the volume is changing at a rate with respect to time equal to 10. Okay. Then it says find the rate at which the surface area is increasing. So you now want to find the surface area is increasing. So you need to find dA dt, okay, when the radius is 3, given r equals 3. Okay. Now everyone take a deep breath. You're probably rolling your eyes and saying you have no idea what's going on. That's totally normal. Okay. You got to just get back into this. So you interpreted two things here. This was a rate of change of the volume, so dV dt. This was, you were asked to find the rate of the surface area, so that's dA dt, because it's a rate, right? And then they told us when r is 3. Okay, so let's see how we do this. All right, let's start with the volume equation. So if I have volume equals 4/3 pi r cubed, I am going to take the derivative of that equation with respect to time. Now, don't freak out. We just did that, right? You guys have been doing this. You can do this. We took the derivative with respect to x of this thing. The only thing that changes is that's not an x, it's a t. So no big deal, right? Take the derivative of v. Well, v is a variable, so the derivative of v is just 1. But v doesn't match t, so you write dv dt. Okay? 4/3 pi, that's just a big number. That's a coefficient. So we're going to do the power rule here. We're going to bring down the 3, and 3 times 4/3 is 4. Pi r to 1 smaller. That's the power rule. But r doesn't match t, so you have to put dr dt. Okay, so the volume of any sphere is that equation. If you take the derivative with respect to time of that, you get dv dt because v doesn't match t, power rule, dr dt because r doesn't match t. Okay, and so now look at this equation. You have an unknown, you have r, that's an unknown, and dr dt is an unknown. So go back to what we wrote down from what they gave us. They gave us dv dt is 10. So I can replace that. 4 pi, they told me r is 3. 3 squared. And then I have dr dt. So that's my only variable I have left. So solve for it. 3 squared is 9. 9 times 4 is 36 pi. And so if you solve for dr dt, you would divide 10 by 9 times 4, 36 pi, which would reduce to, cut that in half, 5 and 18 pi. Okay. All right. I know, just hang in there. So now we know that dr dt is equal to that. What the heck is dr dt? This is the rate of change of the radius with respect to time. Okay. And so the radius is changing that fast, right, at any particular given time. Okay, so let's go answer the question. If you need to find dA dt, you need an equation with a in it, which is right here, and then you need to take the derivative with respect to time, right? What's the derivative of a? It's 1. But then a doesn't match t, and so we have dA dt. Okay, over here, derivative, power rule, bring the 2 down. 2 times 4 is 8. I still have my pi. R to 1 smaller would just be 1. But because r doesn't match t, you have dr dt. Okay. Again, this is just, it's algebra on steroids, but this is an unknown, that's an unknown, and that's an unknown. These are just variables. They're like stuck together, right? That's one variable, one variable, one variable. We know that we're trying to find this. Okay. So the only way I can find it is if I knew r. Well, I do. It's 3. And if I knew dr dt, I do. It's 5/18 pi. And so I could say, well, dA dt is simply equal to 8 pi, that's 3, and dr dt is 5/18 pi. Okay, pi's cancel. 8 could become 4, and that would become 9. And I've got 12 times 5 is 60 over 9, which would also reduce, divide by 3, 20/3. Okay. All right. So what did I just find? I found the rate of change of the area, right, with respect to time, and it's equal to that, right, like almost 7, okay, when the radius is 3. So you've got this balloon. Imagine this massive balloon with a radius of 3 meters, which is like 9 feet. Okay, that's just the radius. And if you're blowing it up at 10 cubic meters per minute, right, what's happening to the surface area? Well, you're blowing up a balloon, the surface area is growing as well. How fast is it growing? Right there. Okay. All right, first one's always the worst. We'll do it again, and by the fourth one, it gets easier. All right, so a person standing in the end of a pier is pulling a boat in, okay, by this rope at a rate of 2. So the thing that you're going to focus on is translating what did they just tell me? Well, they gave you a picture that's L, and you're pulling that in, right, with respect to time at a value of 2. So translating that, you would say dl dt equals 2. It's a rate. So you're going to have this dd, right? The rate of change of L with respect to time is 2. Okay, it says the end of the rope is 3 meters above the water. How fast, that's a rate, is the boat approaching the base of the pier when 5 meters of rope are left to pull in? Okay, so let's start with this one. How fast is the boat approaching? Well, as you pull this rope, the boat is going this way, right? And so X, you can see here, is going to be changing. So they're asking you to find the rate of change of X, dx dt, when, okay, 5 meters of rope are left to pull in. So when this is the rope, so it says when L is equal to 5. Okay, again, FRQ point right there. Simply translating what they give you and writing that down will get you points. All right, so if you are supposed to find dx dt, right, let's just kind of write this down. If you're looking for dx dt, you need an equation with x in it and take the derivative with respect to time, right? That will get more obvious the more questions we do. If you're looking for dx dt, well, I need an equation with x in it, and then I need to take the derivative with respect to t so I can get that, right? Just like when we needed dA dt, I had to have an equation with a and then take the derivative with respect to time. All right, well, there's no equation here, but there is. There's always an equation from some past math class, right, that you guys have taken. This is clearly a right triangle, right? Do you know any famous formulas of right triangles? Sure. Pythagorean theorem, right? Write that down. You know that 3 squared plus x squared equals L squared. How do I know that? Well, yeah, it's not A, B, and C like in geometry, but it's a right triangle. And when you have a right triangle, that's the relationship. Okay. And so I've got this part. I need an equation with x. There it is. Then what? Take the derivative with respect to time. Okay. So d dt. Well, what's the derivative of 9? Just goes away, right? That's a constant. Goes away. What's the derivative of x squared? It's 2x, but x doesn't match t. So dx dt. And the derivative of L squared is 2L, but L doesn't match t, so I have dL dt. Okay? And so this is what I'm trying to find. Well, the only way I can get an answer for dx dt is if I had x and L and dL dt. Okay? Well, let's think about what we got. We've got L right here. We've got dL dt. Okay, so these two are taken care of, but I don't have x. Well, look at your formula right here. If you have a triangle, and that's 3, and they tell you that L is 5, and you need to find x, this is just geometry, right? You know that 3 squared plus x squared equals 5 squared, and so x squared is going to be 25 minus 9, right? Which would clearly give me x squared is equal to 16, or x is 4. And hopefully you guys know the Pythagorean triple, 3, 4, 5. Okay, so that wasn't bad. And so I can fill in. I've got 2. I now know x is 4. I don't know dx dt. That's good because that's what I'm trying to find. Equals 2. L is 5. And dl dt is 2. Okay, so you have 8 dx dt equals 20. And so dx dt equals 20 over 8, which is the same as 4 goes in there 5 and 2 times. Okay. All right. So related rates, and now that we've done 2, all of this looks horrible, but let's focus on where you guys need to spend your energy. I'm going to actually stop it here and do a third one for the other two questions so we can break it up a little bit. So the main thing that you guys are going to find with these problems is writing down what they give you is key. Because if you can list all the details, it gives you a starting point, right? It tells you exactly where you're supposed to start because you're going to write find dx dt. If you don't know what you're looking for, you have no idea where to start. Okay, so that will be the challenge at the beginning. Once you know you need dx dt, then I need an equation with x, right? And then to take the derivative with respect to t will give me that dx dt. Okay, all right. Try to swallow that a little bit, and then I will come back with another video on the last two examples.